Hello and welcome to the wild and wacky world of IBM mainframe operating systems. Today we're looking at OS 390 running on an emulated S390 mainframe. But everything you're about to see is essentially exactly the same on the latest and greatest version of the ZOS operating system and on the multi-million-dollar System Z mainframes that you can buy from IBM today. There's a direct path back to the MVS operating system that was developed for and available on the original S360 mainframe in the 60s. And the fanatical backward compatibility of just sort of building from that and making everything work the same way will rear its head in interesting ways here. So first we'll log on in our 3270 terminal emulator. We'll log on to TSO, the time sharing option, which presents an interactive way to work with the mainframe instead of strictly through batch jobs that were submitted through card readers. And when we're logged in, we'll start up ISPF, I think it's the Interactive System Productivity Facility. So this is really a developer and system manager oriented tool to develop applications on the mainframe. So this ISPF product is what has the text editor, for example, the file editor, as well as utilities and some processes to help you run your various compilers. But today we're just interested in running some SQL commands against DB2. DB2 for the mainframe is also running on this emulated system under OS 390. So to run SQL, I need to put my SQL statements in a file, and then I will execute that file against the database server. You don't just create a file on a mainframe and arbitrarily fill it up with data as needed. You have to allocate a data set. So they're called data sets on the mainframe, not files. And you have to pre-allocate space for the data set, and you have to define some of the physical characteristics of that data set up front before you can then start putting any data in it. So ISPF provides a data set utility. So utilities was number 3, and then data set utility is number 2. Option A allocates a data set, and I'm going to call this data set mwilson dot, let's call it SQL commands. So if I hit enter there, we're going to allocate a data set named mwilson.sql commands. There isn't a hierarchical file system or anything on the mainframe under OS 390 and other MVS derived operating systems. There are just data sets with names on hard drives. And if you look at a particular hard drive, you can see all of the data sets that are in it. But if I don't know what hard drive a data set is on, there are also catalogs. And the catalogs are essentially indexes of all of the data sets with pointers to the right hard drive so that I can refer to this data set by the name mwilson.sql commands without also having to remember that, oh, I created it on the volume user01. So the hard drives on mainframes are called DASDs, D-A-S-D, direct access storage devices. And in this case, I'm going to put it on a DASD volume I have called user01. But then I also have to allocate the space for it. And I can refer to space in terms of blocks, tracks, or cylinders. Newer versions of the operating system, like OS 390, let me work in terms of kilobytes and megabytes. However, these don't necessarily line up to nice, round volumes of cylinders and tracks. And the underlying hard drive and the hard drive controllers and the way the storage allocation really works is in terms of tracks or cylinders. There's a certain number of blocks in a track, a certain number of tracks in a cylinder, and those aren't going to line up with any nice round numbers if I start working in megabytes and kilobytes. So we'll stick with working with tracks. Well, how many bytes are in a track, you might ask? It's a good question, and there isn't one answer because that's entirely dependent on the geometry of the particular model of hard drive of the volume that you're creating this data set on. So user01 happens to be a 3390 volume. That's the current kind of modern standard that, again, dates back to OS 390, but I think even current System Z drive controllers emulate the 3390 geometry. So there will be some particular number of bytes per track, some particular number of tracks per cylinder, and then a total number of cylinders available on the volume. But we're just going to say track. We're going to say that I want to allocate 10 tracks on this DASD, this hard drive, for my data set. If I fill those 10 tracks up, I can add secondary extents, and I'll do that in units of 5 tracks at a time. And I want to reserve 10 blocks in this data set for a directory. Now, this lets me use this data set more as a folder or a directory than a single flat file. And so this helps with organization a little bit instead of a mass proliferation of just this flat structure of files on a hard drive that follow this naming convention of kind of up to 8 characters, dot another 8 characters, dot another 8 characters, to kind of imply a hierarchy. And the end user tools treat that as a hierarchy, but fundamentally it's just one list of files on a volume. So inside of it, I can say, you know what? I want to create named members inside of this file that I can address kind of as individual files. So we'll reserve 10 directory blocks for the index of those things within this file. This is going to be a fixed block record format file. That means that every record in the file is 80 bytes long. We're not delimiting lines by carriage return or line feed. This is essentially just punched card images, which were 80 characters wide. And most of the files you work with on a mainframe that look like text files, so source files like our SQL commands or COBOL or Fortran or C or whatever the file may be, JCL is 80 columns wide. You tend to work with these fixed block 80 byte records. Block size is when I'm fetching records from the physical disk. How much data do I read at once in one fetch? And if I want it to read 100 records at a time off of the real physical storage, I can make that 8,000. So just 80 by 100. I'm going to leave that blank, and the system will pick the value for me, depending on the hard drive type and the size of my records. There is some more optimal and less optimal block sizes just for the efficiency of how the system deals with the data. If I leave this blank, it should get close to the optimum size. So I hit enter there, and I've now allocated my data set. We can see that message up here. Now that that's allocated, I can list my data sets. I can say, show me every data set that starts with M. Wilson, and I can see everything that starts with M. Wilson, and there's my new SQL commands data set. If I scroll to the right with F11, we can see that it is in fact 10 tracks, which is what I requested. 10% used, so this data set is using 10% of its allocated space of 10 tracks. That would be that directory area that I pre-allocated so that I can use this as a partitioned data set instead of just a single flat sequential data set. Currently, it exists in one extent, so we haven't added a second extent, which would get me another 5 tracks worth of space. And it's on a 3390 device, which again is important because, well, how much space is 10 tracks? Unless you know the actual device, and then if you look at the specs for the device to see the physical characteristics, that's the only way you'll know how much space is 10 tracks. And it doesn't really do that math for me. If I get more info on this, I don't think it's going to tell me anywhere like, oh, this is, half a megabyte. I have to know the characteristics of a 3390 device, and I have to run the math myself. You can see it gave us that block size of 27,920 based on the fact that it's a 3390 and I have records of 80. But anyway, this is all a bit of a tangent, but you have to pre-allocate your input SQL data set for the tool that we're going to use. So now that that's allocated, I have essentially an empty file that can hold subfiles, what are called members, that we can put our SQL in. So let's get to the good stuff. Let's go back here to more, and we'll use the DB2 products. And Spoofy is the tool to actually process SQL statements. So my source data set, so we created it, it was called SQL CMDs. And then in parentheses, we have the member name. So let's say create table. 1, 2, 3, 4. Create. I can afford one more character here for the 8-character limit on every name segment. So create table. And because it's cataloged, I don't need a volume serial number. Catalogs and how you find files is a whole other thing. Dataset password protection really isn't used anymore. There's a whole other security product called RACF for the OS 390 and z/OS operating systems, so dataset passwords aren't used. But this is a relic of when an individual user, to prevent other users from being able to read what's in a dataset, could just set a password on a dataset, and if you didn't know the password, you couldn't open up that dataset. So this is one of those relics of times gone by. Output, this will be a sequential data set. Unlike the input, the tool will allocate this for me. So we'll just leave that as mwilson.sql.output. That worked before. Don't need to change the defaults. We want to edit the input, and then we want to execute it. And then if it succeeded, we'll auto-commit it, and then we'll look at the output of the SQL commands when we're done. So I hit enter here. We end up in the editor editing mwilson.sql commands, member name, create table. This is the ISPF editor. So if you are editing files on the mainframe, this is probably what you're using. And it's kind of a weird, it's VI-like in that you can put line commands in this red area, but it's not VI-like in that it's not modal. You're not in like insert mode versus command mode. So the red is where the line commands go. Under the blue is where the actual text goes. Since we're working with SQL, I can tell it, you know what? I want this to be mixed case. So I think I can say caps off. Otherwise, it will just convert everything I type into capital letters because, until recently, punch cards didn't have uppercase and lowercase. It was all capital. So the mainframe operating systems, most things tend to be in capital letters. This is where it's kind of like said VI-like. I can say I20 for insert 20 lines. That gives me 20 new lines to work with here. And I will just start typing my SQL. So create table. Let's say I want to keep track of my favorite books. We'll have maybe an ID, which is an integer, and say not null. And then my title, varchar. How long are book titles? Also not null. And author. And yeah, maybe we allow a null author because maybe it's published anonymously or something like that. Who knows? Give it a primary key for the ID column. That should do it for that. Now, unlike most database systems I've worked with, we have to say in database and then my database name. So MRW DB001. And a semicolon to end that statement. We can use comment lines, SQL comments, or 2 dashes. If I don't say in database MRW DB01, everything applies to the default database, which is just a system-wide default database that you may or may not have permission to do things in. So there is no context where I'm connecting to a specific database on the server. I actually have to qualify this command when I'm creating a table with, well, okay, what database do you want to create that table in? Now, as a user, I'm running this as my user mwilson. It will namespace qualify this table for me. So it will be, why can't I go into insert mode? It will be mwilson.books behind the scenes, but I can just go ahead and leave it as books for now, and it'll do that. So once I've done that, I should be able to insert data, right? So insert into books, values. Let's say book 1 is My Neat Book by Matthew Wilson. You can tell I'm going to be a great author. insert into books values. Let's do another one. Another thriller by, I don't know, Jane Smith. That looks good. So I'm creating my table, and I am inserting a couple of initial records into it. So if I exit the editor, it tells me that the edit session is completed. Press enter to continue. That's to continue on to the execute phase. So we will execute this. And now we get the output. So it echoes back the statement that was input. We see statement execution was successful for our create table books. That's good. Insert into books. Error -540. The definition of table in Wilson.books is incomplete because it lacks a primary index or a required unique index. So even though I said primary key ID, DB2 doesn't automatically create the index on the primary key for me. And I don't remember if I mentioned earlier either, primary key doesn't imply not null. If I said ID int primary key here, I would have gotten an error that said you can't create primary key on a column that's not null. So everything is very, very explicit. No indexes are created automatically. No column becomes not null because I said it's the primary key. Things you're used to in other databases don't happen here. And again, that seems to be the theme of the mainframe, right? It's like, oh, you have to pre-allocate your data sets, your files, and you have to say how much space you want to allocate for them and how you physically want them arranged. Yeah, welcome to mainframes. So that failed, so it performed a rollback. That rollback succeeded, so I guess that's good. SQL statements assumed to be between columns 1 and 72. We'll look at why that is in a moment, even though this we said was an 80 byte record size. Okay, so we exit out of that, and if I just hit enter again now, we're back in the edit phase. I'm back in that same file that we saved before, and we know we need to create our index. So create index, we'll call it books primary key on books ID, and actually we need to say create, and this is, I have to delete space off the end of this line here, so because the line can't be more than 80 columns wide. So now that I deleted that empty space, I can flip over into insert mode here and create, there we go, create unique index books pk on books ID. Does that look good? I think so. We will exit. We will hit enter again to execute that file we just edited. And let's see what happens. Table created successfully. Remember, we rolled back the last transaction, so we're not getting a duplicate table error here. Create index, successful. Insert books, successful. Insert books, successful. Excellent. All of that was successful, so we committed the transaction, and that's the end of the input. So now, as one last thing, let's say we want to keep that create command around. So we'll make another member for select data, and this we will just say select star from books, and exit out of that, run that, and there we are. Select star from books. We get the nice column header, ID, title, author. I can see my books, and that's pretty much what we expected. That matches what our inputs were. Another thing we can look at, DB2 admin. Again, who needs Management Studio when you have this, great console-based interface and you're just making files for your SQL input, running them, seeing text files of the SQL output of that series of commands? This is great, so efficient. DB2 system catalog, I can see, for example, the databases in my system. Look at that. We can restrict this to that database, MRW DB001. There's the database that we were just working with. I can display the tables in that database. I can see we have our books table. That's good. I can look at the columns that are defined in that table. There we go. There's our columns. Who needs a sidebar with all that information when you can just browse around this way, right? If I look at yeah, so I'm on books. So from right here, I can drop that table. Drop table in Wilson.books. Boom. Gone. Yeah, so if we go back to our dataset list in Wilson, we can see now my my output file is still there, right? That's just, it saved my last output to a file. If we look at my partition data set, we have the two members, create table, which was the first one I created, and then that last one, select table, right? If I look at this file, we have the text that I saw, but remember we had those 6 or 7 columns for or character positions that were where my line commands go. So we weren't seeing all 80 characters of our records. We were only seeing 72 characters of our records when we were in the editor. Well, the last positions, 73 through 80, are line numbers, card numbers. And the SQL processor knows to only use positions 1 through 72 as SQL input, because the rest of the record are these sequential numbers, or the ordered numbers. And this was for when you dropped your stack of punched cards and they got out of order, you always punched them with a sequence number on the end so that you could drop them in the physical card sorter and then get your cards back in the correct position. So the editor behind the scenes, because even though this is all just files on hard drives, it still thinks we're in the punched card world because we're on a mainframe. The editor put in these numbers for me. And when we went back later and added in new rows, like to create that unique index on books for the primary key, you can see that we ended up, inserting numbers between the sequence of numbers that were there. And there's renumber commands if you want to get a nice new, set of numbering from the start. But it's kind of funny to see that after you're editing the file, and you just come back and view the file, not in the editor. You have your card numbers so that if you drop your stack of cards on the floor, you can drop it back in the sorter and get them back in the right order. So that's about all there is to show here. Yeah, wild and crazy world of the mainframe. We will log off and you can get back to your regularly scheduled modern computing.